Hi folks, this is the second video segment that I am doing to discuss the issue of the sensors when you use Catia to do finite element analysis. In the first one I discussed the reaction sensor and the applied load sensor, and right now I want to talk about the local sensor. The problem that we are looking at is simple. So we have a shaft 10 inches long, and I think the radius, I'm not sure what the radius is, but we'll find out. I think the radius 0.1 inch. Let me actually check my MathCAD program to see what radius am I using here. The radius is 0.1 inch, correct. Okay, so make this thing bigger. Right here, 0.1 inch, length is 10 inches. And one end of it is clamped, and the other end, at the other end, we are applying a torque of 10 pound-inch. Torque of 10 pound-inch. The analytical solution for this problem is available from elementary strength of material textbooks, and basically, if you assume steel, this is almost the Young's modulus of steel, its default value in Catia, Poisson ratio for steel, shear modulus of steel. The polar moment of inertia is pi r to the 4 over 2, and the infamous formula tau equal to tr over j is going to give you this is going to be the shear stress to torsion. And this is the only stress that's acting. So if you plug in the von Mises stress formula, you get von Mises stress is √3 of this value. So for the numbers that are given, the shear stress is almost 6,300 psi, and the von Mises stress is almost 10,000 or 11,000 psi. And the angle of twist is TL, the torque times the length over G shear modulus times J, and that'll give you in degrees for that particular data, almost 3 degrees, and right, and the displacement of the extreme end is going to be that angle, that maximum angle, times the radius, and it's going to give you a tiny little displacement of that value, inches, magnitude of displacement. Okay, so first of all, let me all the properties are applied. Let me show you what the load is. The load, right click here, and let me show that. I'm applying it as a concentrated, as a load applied to that end, to that face, directly applied to the face, and the value was 10, right there, 10 pound-inch. There will be a follow-up video where I discuss the concept of virtual parts, rigid virtual part and smooth virtual part, where there are other ways of applying the load to this. But this problem is simple enough, we can apply it to that face. Okay, let's run this thing first of all. Right there. Okay. And by the way, I want to show you the mesh size here. So right click, let me show you the mesh first. You can see it's very fine. And I believe I'm using, if I'm not mistaken, I'm using parabolic element. Fine. Okay. Deactivate the mesh. Let me now go and plot the von Mises stress. Right click, activate it, and it looks like that. Let me change the rendering here to material shading. Right there. Is there something else showing up here? Let me see. All right, let me delete this. Let me look at the displacement first, right there, and change the rendering here. Average ISO. Oh, I know what the problem is. On this laptop, my video card is not working, so let me go ahead here and change it to linear. I think parabolic one, when it comes to displaying the contour plot, shaded contour plot, you're not going to see that. So I'm going to rerun this thing with linear one. Linear one is okay. I don't have that problem. I don't think, at least I don't think I have that problem. We'll see. I might have it. Okay, so let's look at the displacement. Oh, there. See that? That's better. Okay, and von Mises stress. Deactivate. Oh, I still have that problem. No, it's not. It's not. This is the issue, because the elements are linear. It looks like that. But you know what? First of all, let me change my element size from 0.05 to 0.01. If I was doing it with the parabolic one, I wouldn't have that issue. But since I can display the parabolic shaded contour, I have to use a smaller element size. So let me run this thing. It's going to be very small. May take a little bit longer, but they are linear. Okay. Just wait for a second. Actually, I'll have an idea of what the number of elements and point nodes are. We're gonna check that, because this is so small that they have a lot of elements. I won't be surprised if it's maybe 100,000. We'll find out. I haven't even run it yet. This was pre-processing. Yeah. On this computer, when I run parabolic elements, it runs and the numbers are okay, but when it comes to displaying the plot as a shaded image, something goes wrong. But I don't think I have. I don't think I have that problem when I use linear elements. The only problem is that to do it with linear elements, you have to have a lot of them, and you can see the consequence. Okay. Let's give it a couple of minutes. I'm sorry this distracts you from that whole concept of creating sensors, but I don't have much choice. Let's probably take another minute or so. All right, good. So let me see now. Translation. Remember how it was jagged? See, even this one doesn't look right. Oh God. So deactivate this. Let me look at the von Mises stress. I'm really sorry. You see, these blue colors don't look right, and they're not supposed to be here. It's supposed to be something like that. So temporarily ignore the fact that I have this bluish thing. You can see that. First of all, let's go and do the following. Let me not do it as a shaded image. It's like this. This is supposed to be all blue. This stuff is not supposed to be here. Now, I don't know whether I can. There's anything I can do with these, but all right. Let's go ahead and see what's happening here. First of all, the pattern must be circular, and it is. Okay. Now, let me deactivate. See how it works. Let me deactivate these plots. Okay. Deactivate. Okay. Now, we go to here to sensor. Right click. See that? Create local sensor. Local sensor. You click on it. It says, well, what is it that you want to plot? So let's say I want to plot the von Mises stress somewhere locally, okay, not on the entire model. So I say von Mises stress, and we say OK. So what happens here is, let me delete this. Okay, this is what I just did. Okay, von Mises, but there's an exclamation mark here. You double click on it. It says, okay, well, where do you want to plot this thing that you're asking for? Well, I want to plot it on that face, or yeah, on that face, for example, or on that face, etc. In my case, let me hide this these loads, okay, or on that edge. See that? On that edge, or on that face. So let me select the edge right there. See that? It says one edge, one Mises stress. Okay, and then you say, all right. Now this one, there's no exclamation mark, but it needs to be updated. You put the cursor here, right click, update sensor. You click on it. It says it takes time, that's fine. You say okay. And notice that there is no exclamation mark here. Now, what can I do with this thing that I just did? Well, right click, I can say export data. Export data. So I'm going to put these numbers, in other words, the stuff that I recovered from my sensor, local sensor, either in a note, on a text file or an Excel file. I'm going to put it in an Excel file, right there, Excel file. And then I decide where it's going to go. Well, it's going to go to the desktop. It's going to go to my desktop. Okay. And I'm going to give it a name. I'm going to solve it. I'm going to call it export data file. Why don't I call this thing the von Mises VM on circular edge. Circular edge. Okay. So give it time. So it's going to put the coordinates of those nodes, the nodes on that edge, and the corresponding von Mises stress in that Excel file. So let's go and check it out. There it is, export data. Let's open it up. There we are. So we have the x coordinate, the y coordinate. Remember the y coordinate is 10 because it's the, and the value of the von Mises stress on that edge in the last column. Okay. Now these are things that can be compared. Remember this. This was, these are the things that we can compare with the MathCAD calculation, which is right here. Now you have to be careful because there is no, we did not do any accuracy study here because I don't know whether those elements are good. In fact, if you look at it, this should be 11,000. Elementary strength of material says von Mises stress should be around 11,000. But if you look at this, if you look at the plot here, if you look at the plot, where was it? Sorry, this one got Mises stress, although it doesn't look good. But you see, there are big stresses around here because of the way we have applied the load. But over there, just put the cursor on it, you can see that they're all of the order of 11,000. 10,400, etc. But when you get close to this edge, and this is the edge that I picked, okay? This is the edge that I picked, the numbers can be very large here because of the inaccuracy in applying the load. Now let's do another one. So deactivate this. So let's say that let's go ahead and do exactly the same thing at this end. Okay, the one we stress at this. Actually, let's do it on this. Where is it? On this face. So let's say you want the one meter stress on this face. So we're going to say right click, create a local sensor, 1 meter stress. Okay. Double click on it. This time let's select this edge, the edge over here. And we say okay. And update sensor. And export it. This one, the clamped edge. Circular edge, okay? Okay, let's go and find out. There is the clamped edge. And you can see at the other edge, because we don't have that applied, applied moment as you see, as we did it there, they're much closer, they're more uniform and closer to the 11,000 target value that we get. All right, I want to show you. I want to say one more thing. You can do. Let's also do the angular. Oops, cancel that. Let's also do the displacement. Okay, so let's go ahead here. Go to the edge on the other side. Oh, where is this? The edge on the other side. Okay, one more local sensor. So right click, local sensor, displacement magnitude, right there. Double click on it, select this edge. Okay, say okay, and update. And now export. This is going to be displacement, tangential displacement, that's what it is. Tangential displacement, magnitude of the displacement. Okay, give it time. All right, let's go and open that file. So we have the x coordinate, y coordinate, z coordinate, and there is the displacement, almost 0.005, and it's not as sensitive as the stress was, so they're all like that, 0.0054. And if you compared it with the MathCAD sheet, right there, 0.0055, etc., because it's the radius times the angular rotation. One last comment that I want to make, and this really bothered me when I was a student. Let me plot the shape of the deformed shape. Okay, so since my colors are not good here, so let me actually go ahead and plot the displacement field like that, and double click on this. Where is that? Change the scale to default. What do I want to show you here? Sorry, not there. Just 1 second. Well, let me see for a second. First of all, let's look at the elements. They're so small. You'll see that they're so small that it's all black. But the thing that I wanted to show you is let me see for a second. Now, because of the length of this, it may be hard to see it in this particular problem. So let me do the following. Let me go and change the size of this. Instead of 10 inches, let me make it maybe 5 inches. This is so long that you cannot really see what I have in mind. So let's go here and to the part. And the pad, instead of 10 inches, I make it maybe 1 inch. Looks like that. Okay, back to analysis. I don't have to use such a small size here. I'll make it, well, actually, that's fine. So let's run it. All I did was the length of this is instead of 10 is 1. Obviously, it's going to run a lot faster because there's not as many elements. Okay, so let me plot for you deformed shape. Yeah, this is still let me go and change the size of the element here. This is point, I'll make it 0.1. Run it. I want to show you an artifact and explain to you what I have in mind. Oh, this is too big. 0.05. The radius was if I'm not mistaken, the radius was 0.1. Okay, so let's make this thing 0.05. Run this thing. If I can succeed in doing this thing, I'll just give it up. Okay, just a second. I think I know what the issue may be. Let me change the size of the moment. Let me put a couple more zeros here. Yeah, I think that's what I should have done. I should have used a bigger moment to show you what I have in mind. Well, I guess not. Oh, there. That's what I wanted to show you. You see, it always bothered me that torsion, a torsion problem, it's correct, but it looks like that. This always bothered me because I know that this is not supposed to happen. The reason you get an artifact like this is the following. Remember, I applied the moment, I increased the moment here so that I could see it. With the moment that I had before, the displacement was so small that it was unnecessary to magnify them. Okay, but here the displacement are magnified by a factor of, let's see, by a factor of 8. Okay, you can see that factor of 8. So this end is fixed, no displacement, no rotation. But this end, there is a rotation, and it's magnified by a factor of 8. That's why you get the impression that actually it's getting fatter here. That is really not the case. This is an artifact that one should be careful not to be too concerned about it. That was not the purpose of this video segment. It was showing you how to do local sensor and update and export the data, but I also wanted to point out to this this thing that doesn't look right to people who are doing it for the first time, but it's okay.